Hi everyone, my name is Cesar Santoyo, and I'm presenting our work titled Multi-Level Electric Vehicle Charging Facilities with Limited Resources. This work was a collaboration with my research group's postdoc Gustav Nilsson and my research advisor, Professor Sam Coogan. The electric vehicle market has grown and continues to grow. Bloomberg New Energy Finance releases a yearly outlook on the electric vehicle market. In their 2019 study, they predict that by 2040, the United States new vehicle sales will be comprised of 57% electric vehicles, while globally the passenger vehicle sales will be 30% electric. As you can see in this plot on the upper right-hand side, you see a gradual decrease in the market share of internal combustion engine vehicles, otherwise known as ICE vehicles, while plug-in hybrid electric vehicles, otherwise known as PHEVs, and battery electric vehicles, otherwise known as BEVs, have an increasing market share during the same time frame. Much of the increase in market share of electric vehicles is driven by a drop in price in lithium-ion battery packs, which is reflected in this plot in the bottom right. The drop in battery pack prices is also reflected in the electric vehicle prices themselves and is catalyzed by a variety of government incentives. The increased adoption of electric vehicles leads to a series of questions. For example, what are optimal ways in which charging facilities can adjust their pricing schemes to best serve their customers? Additionally, how do charging facilities properly manage space and power limitations? And how can they guarantee that such space and power limitations will not be exceeded? So the main takeaway here is that the increasing adoption of electric vehicles calls for better management of EV charging facilities. To address the aforementioned questions, we construct a framework within which we solve these problems. Consider an electric vehicle charging facility which has a finite number of chargers and a finite charging rate capacity. At this charging facility, users arrive according to some probability distribution. Specifically, we model this as a Poisson process. A user J arrives at a charging facility with some demand X subscript J and an impatience factor alpha subscript J, which quantifies how much a user values their time. A charging facility has capital L levels of service and broadcasts the price per unit energy and the charging rates at each particular level of service. It is important to note that the user side contains all of the stochastic aspects of the problem, while the charging station has fixed L levels of service. This formula evokes the questions, which level of service will a user J choose? To further explore this problem, we define the function g, which quantifies the cost of charging to a user as follows. G subscript cursive L is the total cost faced by a user at the cursive L level of service, and it's a function of the user demand, X subscript J, and alpha, which is the impatience factor. This total cost function has two aspects to it. The first part is the level of service cost, which is directly driven by the demand of the user and the cost per unit energy at a particular cursive L level of service. And then there's the personal cost to the user, which is directly driven by the impatience factor, and it's a product of the impatience factor and the time spent at a charger at a particular level of service. This time is xj over r superscript L, and we denote it as U, and its units are in hours. The function g is a function of random variables, and hence the user choosing a particular level of service, cursive L, can be thought of as a discrete random variable. Also note that the probability of choosing a particular level of service is equivalent to the probability of choosing some rate r superscript cursive L. The users seek to minimize their cost by minimizing this total cost function g subscript cursive L. This brings us to the problem we are trying to solve. Provided probabilistic bounds that the charging station does not exceed user and power consumption constraints. So to address this problem, we first need to make a series of assumptions on some of the random variables and some of the charging facility parameters. First, the charging rate demands and the user impatience factors are all bounded, independent, and identically distributed random variables. This is a necessary assumption because we make use of concentration inequalities, as we will see later on. The second assumption is faster charging rates are more expensive. So given capital L levels of service, they are ordered in such a way that a rate R superscript I greater than R superscript K implies that the cost per unit energy of I is greater than the cost per unit energy of K, which makes sense. In a real world application, faster charging will cost or may cost the user more money. And third, the third assumption is that users are rational. In other words, users leave the charging facility when their charging is complete, and they seek to minimize the total cost to themselves. Now, returning to the pricing function, how can we use this pricing function formulation to provide guarantees on the charging facility capacities? The pricing function and choice of level of service of the user specifically relates to the likelihood the maximum power draw of the charging facility will adhere to the capacity. And here we note that choosing a particular level of service it relates to a user choosing a charge rate where R subscript J is the choice of rate, which is the argument of the total cost function. The total cost to a user is linear in both the variables alpha and x. It turns out that the probability level of service will be the minimum is an integration over the probability density function of the impatience factor alpha. What this means is, given a set of 5 pricing functions, so 5 levels of service at a charging facility, the probability take level 2 is the minimum, is an integration over the probability density function of alpha over the region that the price level, the level of service 2 is the minimum. The full proof of this is available in the IFAC paper, and because as a result of the ordering of the rates where R5 is greater than 4, etc., makes this a clean expression. Here it is worth noting that while we have been interested in the probability that a user will choose a particular level of service, we have simultaneously formulated a method of computing the probability that a particular rate will be chosen. Knowing the probability of a particular rate will be chosen provides a segue for computing the probabilistic guarantees on the total charging facility charging rate being adhered to. We formally define the probabilities we are interested in other words, the probabilistic guarantee. So define A of t to be the number of active users at a time t, and Q of t to be the total power consumption at a charging facility at some time t. Furthermore, let mathcal m be the maximum allowable users, and mathcal r be the maximum allowable power draw of those active users. Then we are interested in computing the probability that the user capacity is adhered to, which is this top probability, and the probability that the total charge capacity is being adhered to. And we're interested in computing a minimum, a lower bound on both of these probabilities. Note that the probability that the number of active users at some time t is less than m is greater than a value that is a function of the user capacity. This follows intuition because, in other words, the larger the charging facility user capacity is, the higher the probability the number of active users at some time t will be less than the user capacity. A similar thought process holds for the total charging rate Q of t. However, note that Q of t is a random sum since the chosen rate of charge itself is a random variable, and the number of terms, which is the number of active users at a given time t, is also a random variable. To find these probabilities, we make use of Bernstein's inequality, which is a type of concentration inequality. Here, using Bernstein's inequality, we derive the function delta m. So delta m, notice that as m gets very large, delta m starts to approach 0 when m is greater than the product of the Poisson rate times the expected value of the time spent at the charging facility. And this follows our intuition, since the lower bound on our probability of adhering to the user capacity rate is 1 minus delta m. So since this approaches 0, as m gets lower, that means it is less likely, or we have a higher confidence that we will stay within our user capacity threshold. Similarly, for gamma r, we can compute a similar function that as r gets larger, gamma r starts to approach 0 as well. But this formulation is a bit more complicated due to the fact that the power draw of the active users is a random sum itself, and it depends on the previous bound delta that we derived. The full proof of delta of the function for delta m and gamma r is available in the IFAC paper, and how Bernstein's inequality is directly used is also detailed there. But the main takeaway from this is that given a charging facility's operational limits, we can compute confidence intervals on the likelihood we will adhere to such a limit, or a lower bound on those probabilities. So now that we have derived these bounds and mentioned that there is some conservatism associated with them, we analyze how conservative the bounds really are relative to a Monte Carlo simulation. Here on the left, we see that the bounds are not so conservative for the number of active users. So how do we interpret these bounds? So m on the x-axis we have the user capacity, and on the y-axis we have the 1 minus delta m, which is just the lower bound on the probability. So let's say we're interested, we have a user capacity of m equals 40. Our bounds predict that the probability of us adhering to this bound is greater than about 0.85. And comparing it to the mean of several Monte Carlo simulations, that probability comes to about 0.95. The error bars here represent the minimum and maximum values attained at that particular percentile for the Monte Carlo simulation. A similar exercise can be conducted for the charging rate and analyzing the lower bound on the probability of adhering to the total charge rate limits at a particular charging facility, and seeing that it lower bounds the Monte Carlo results. So how are these results useful, and how can they be used in practice? So here we illustrate a charging facility where in blue is what we'll call our original charging rates, R1, R2, V1, V2, and the resulting 1 minus delta m and 1 minus gamma r bounds are highlighted in blue in the right-hand plots. Now let's say a charging facility operator would like to increase the confidence that the user capacity limits will not be exceeded. So they look at around m equals 40, and they see it's around 0.8, 0.9. So to deal with this, the charging facility operator increases the charging rates, which results in R1 plus and R2 plus. And the resulting cost functions are outlined here. And the resulting 1 minus delta m lower bounds on the probabilities are seen in this red dashed line. So what we see here is that increasing the rate increases the lower bound for m equals 40 for adhering to the user capacity constraints. And this is a result of increasing the rates, or the charging rates. However, this comes at the expense of lowering our confidence that we will adhere to our total charging rate capacity at the charging facility. Of course, a similar exercise can be conducted by reducing the charging rates to shift this, which will come at a cost of the number of active users. Of course, in practice, a charging facility operator will play with this formulation and tweak the charging rates to see what best fits what their operational limits might be. So, making some assumptions, we can quantify the confidence intervals on the number of active users and their energy consumption rate. So the results we present give a practical method for facility operators to set electric vehicle charging rates, and we illustrated that with an example. And that is all, and thank you for your time.